Welcome everyone to the first of 3 lectures on biostatistics for clinical and translational researchers. My name is Jo Wick, and I am a faculty member at the University of Kansas Medical Center in the Department of Biostatistics and Data Science. I will be and am currently recording the lectures, and I will send out links to registered participants by email. These will also be housed on the Department of Biostatistics and Data Science website, kumc.edu. You're also welcome to reach out to me personally by email if you need something regarding this class, either currently or in the future. So the objective of the class is not to make you a statistician, but to make you knowledgeable of how statistics plays a role in evidence-based medicine, and how it's also a huge component of rigorous science. So if you're interested in participating or leading rigorous science, you need to be able to speak the language of statistics and have an idea of what it is that it brings to the table to ensure that your studies are producing valid results and are generalizable. In the 3-part series, again, it in the past has focused a lot on just how do I analyze this data? How do I know the right number of samples I need to collect in order to answer a particular question? We'll still cover that kind of material, but we're also going to focus on rigorous science this year. We're going to understand the strengths and limitations that are a function of features of these different kinds of studies that could be conducted. So we'll break them down based on the different characteristics of the study design and how those characteristics either strengthen or weaken the evidence that's produced by that kind of study. We'll also briefly distinguish between how we can infer causation and when association is more appropriate, which requires us to, again, understand the roles of what's called chance or random variation, bias or systematic variation, and confounding in the evaluation of our own research and the research in the literature. Before we get into the material, though, I wanted to take this opportunity to talk to you about other opportunities for building your training or your education in clinical and translational science that currently exist at the medical center. For those of you who are just interested in opportunities like this class is offered every summer, usually Friday mornings in July. It does change slightly from year to year, but the material is always recorded and posted and freely available for you to access on the department's website. If you want a little bit deeper dive into some of these concepts, you're welcome to take a look at the course catalog online, and you will find a variety of graduate level classes in biostatistics, either kind of a general treatment of the subject or a specific, very deep dive into a particular method like linear regression, analysis of variance, non-parametric statistics, multivariate statistics, survival analysis, those kinds of things. There are courses in epidemiology, courses in data management, and in grant writing. If you're interested in more than one class, you might want to consider a graduate certificate, and there are graduate certificates offered by our department and other departments on campus that would allow you to pick and choose from, let's say, 3 to 4 courses in these topic areas and actually get transcript credit for those in addition to a graduate certificate. That information can also be found at our website, or it can be found in the KU catalog. There are graduate programs. You can actually get a master's degree in clinical research through the Department of Population Health and through the CTSA. KL2 Scholars Program, TL1 trainee programs, these are mechanisms to facilitate scholars and trainees, junior faculty, to get this additional training in clinical research. There are also online resources that are nice and free, and you can access them at your convenience. And I think that there are, I could create a list that's almost endless of things that I have found useful in developing these slides over the years, but you might want to consider taking a look at a couple of these that I've prioritized for your reading. And I will have them linked to in the slides and get these sent out to you all so you can access them directly. There are also free tools. I know that a lot of specialties have specific types of software that you use that are geared toward the things that you all usually do with your data. But there are more general tools that are really nice for visualization of data, data cleaning, merging, filtering, sorting, and analysis. RStudio being one of those. RStudio is a company that has developed a more user-friendly interface of this language called R. And it's basically, again, for performing descriptive and inferential statistics, but it can do many other things. And they've created a whole set of training videos. So for those of you who are interested in learning more about how to do this on your own, RStudio is a great resource. So today we're going to talk about rigorous science. Rigorous science is the type of science that's reproducible. It's the kind of science that we all want to do. And I think it's important, so important, that we begin with it and a select set of topics related to this, that we're going to do this first. And in part 2, we're going to get into study designs, strengths, limitations, and the common statistical methods that are appropriate for those kinds of designs. We'll begin with randomized controlled trials and go all the way through cross-sectional studies and case series and case reports. And then we will talk about meta-analysis and talk a little bit about how we analyze the data from those particular types of studies. In part 3, we'll get into statistical methods. So we'll talk about things like t-tests and linear regression, ANOVA, survival analysis, and we'll go through examples. So scientific rigor, what is rigorous science? Well, rigorous science is the science that results from a proper application of the scientific method. It involves using theory and very controlled experimental approaches to produce data. It has to be undertaken in a way that it will enhance confidence in the accuracy of findings. So there's a figure here that I really like. It's kind of the pentagon of scientific rigor, and it shows you all of the different pillars that make up rigorous science, and if one or more of these is flawed, then we end up with studies that may not be reproduced. For instance, intellectual honesty, that's a part of scientific ethics. Experimental redundancy just means that we prefer to replicate a finding in an independent study before we really truly trust the finding. Logic, probability, and statistics. We're going to focus mainly on the probability and statistics pieces, but we'll also touch a little bit on questionable research practices, which can get into a little bit of logic fallacy and intellectual honesty. So when we talk about rigorous science, it has a couple of characteristics. The first characteristic that I'd like to focus on is the fact that rigorous science is repeatable. What I mean by repeatability is that the methods used in a study should be exactly reproducible. We should be able to take your protocol for a study and implement it as exactly as possible with the same data and tools to obtain the same results. So the idea is you are transparent, you preserved all of your original materials, you have detailed methods, and we all know that science includes subjective decision-making. So we have to have written justification of all the decision-making so we can understand where there might be strengths or flaws in that process. And then, of course, sharing your data and sharing your code. There's a great editorial, I should say, in PLOS Computational Biology, and I'm not a computational biologist, but it's 10 simple rules for reproducible, computational research that I think is broadly applicable to all fields. And again, it gets back down to organization, transparency, and preservation of materials. So if we can do that, then there's no reason why someone could not take your data and your materials and methods and reproduce exactly what you reported. That's actually becoming a standard for some journals, is that you share your methods and your code so that they can independently reproduce your results. I know it's a requirement of the Food and Drug Administration for drug approval. So companies that are producing medicine are required to provide that information to the FDA. Another aspect of rigorous science is the fact that it's reproducible. So repeatable versus reproducible. And this is my definition of repeatability and reproducibility. I want to warn you that if you go out to investigate this in the news, in the literature, you might get slightly different versions, but this is and one definition used of reproducibility. So as opposed to methods reproducibility, which relies on transparency and openness, results reproducibility, you sometimes hear called replication. And that's the ability to take the same methods, apply it to new data, and produce a corroborating result. So a similar result, not necessarily the exact same, and they won't be the exact same, but if in an initial study they found that there was a positive association, then the new study, taking the exact same protocol but producing a new sample, will produce, again, slightly different data. And as long as you find that same positive association, it might be stronger or slightly weaker, then you've corroborated the results. And that's the idea behind results reproducibility. Often, again, this is where the focus is in terms of reproducible research. So how do we ensure that we have the ability to replicate a result in a new independent study? Well, the first is replication, reproducibility, depends on the fact that the study is repeatable. So if your study doesn't have that first characteristic, that you were transparent and open and organized and clear about your methods, if you did not conduct a repeatable study, it will not be reproducible. The second and third characteristics are the things that we usually learn about, and that's the idea of internal and external validity. Internal validity just means that the results produced by the study are accurate. They're unbiased, which means that they've hit the target. They're very close to the truth, and they're precise, which means there's not a lot of uncertainty in the finding. It's a high-quality finding. If a study is externally valid, that just means that that result, assuming it's internally valid, it's precise and accurate, can be applied to different populations and settings, that it will translate to different populations and settings. So another thing to think about is this idea that rigorous science relies on the proper application of the scientific method. And if you're paying attention, if you've been paying attention for several years, there's been a lot of editorials and discussion about the fact that a lot of science is not reproducible. We conduct a study and it finds a positive association. A second study's conducted and it doesn't find a positive association. It finds no association whatsoever. So why would that be? And we're going to talk about today why that would be. One of the reasons why that might be could be that we're messing it up for ourselves. And there are no shortage of opportunities to do that. So what you see here on the right side of the screen is the scientific method as it pertains to clinical and translational research. We observe things occurring which generate testable hypotheses. We design studies around that. The studies produce data. We analyze that data and test our hypotheses, interpret the findings, and then we disseminate that information, which then further provides accumulating evidence to update and create or generate testable hypotheses, and this cycle is never ending. How could we mess it up? Well, we might do some observation and generate hypotheses that aren't testable, and there are hypotheses that are not testable. We might also have something called hypothesis myopia, in that we fixate on the things that we believe in our guts are true and fail, for whatever reason, to see that other hypotheses are just as likely as the one that we're really excited about. In terms of the study design, this is, again, where we often focus on the flaws, but we need to think beyond that. We could, again, fail to control for sources of bias and sources of error in our study design. Sources of bias are any sources of variation in the study's outcome that systematically push it away from the truth. They make the association look positive when there is no association, or they make it look negative when it's actually positive. And then sources of error just increase the variation in the outcome. So maybe what it does is it buries the signal in a lot of noise. And if we know about these things in advance, we can control for them in our study design. The things that we don't know about in advance, we can actually implement other features of experimental design to help minimize the impact for unknown sources of bias and error. One of the consequences for failure to control for error could be that your study is what's called underpowered, and that's exactly what I just indicated, that you might lose a treatment signal, a treatment effect signal, in too much noise. And it could be, again, because you didn't have a large enough study to overcome the amount of variation in your data, or it could be that there were unknown sources of error that masked the signal. You could also be overpowered. Why is that a problem? It seems like a very powerful study, one that is technically too powerful, would be a good thing. Well, there's a lot of reasons why it wouldn't be. We're going to learn about one of those today, and that's the p-value. The p-value, it turns out, it's a great metric for us to determine whether or not a signal is statistically significant specifically. And if our study is too powerful, many p-values will be small, artificially small, and make us believe that there is a significant association, one that may be impactful, when in fact your p-value is detecting noise because you have too much data as opposed to not enough. The other issue with being overpowered is an ethical issue that we will touch on at some point. Not using blinding, blinding of the participant, blinding of the evaluator, blinding of the statistician, and again, this is not always possible, but when it is possible, it should be used. Not using randomization, again, another feature of experimental design that is not always possible, but when it is possible, should be used. It protects us against bias. Blinding protects us against bias. All of these features protect us against bias and error. In terms of the data collection, there's lots of things that can go wrong. Maybe quality assurance, quality control, there is none. And so you end up with inaccurate measurements or inaccurate data entry. You could also end up with missing data for whatever reason. And all of those things, again, can impact the internal validity of a finding because they're going to produce bias in our assessments. For analyzing data and testing hypotheses, first of all, we want to make sure we're using the right method. And this does come up a lot. We learn about some pretty well-known approaches to data analysis, and for whatever reason, we end up applying the wrong one because we don't realize that there's kind of a method to the madness. So wrong methods produce wrong results. We want to make sure that we are applying the correct method, and we also want to make sure that we understand the individual method's strengths and weaknesses, which we'll get to in part 3. For instance, the t-test requires some things of the data before it will produce a valid result. And if you don't verify that those assumptions hold up, It will still produce a result, but the result will be incorrect. Something called p-hacking. Again, today's talk is going to focus a lot on p-values, their strengths and weaknesses, a better interpretation of what they actually are. P-hacking is also known as phishing. It's basically not using p-values the right way, or using them in a way and you're not honest about the way that you're using them. So p-values were really designed for prospective studies that were rigorously designed, where all sources, potential sources of variation and error, have been accounted for in the study design. P-values are usually associated with hypotheses that the study was powered for. So if you're using a p-value in a different way, that's called p-hacking, and it's not necessarily wrong to do that. You could think of using the p-value as a signal for a potential hypothesis that should be tested in a study that's designed to test it. But not being honest about your use of p-values in that way, making it sound like it was a confirmatory analysis as opposed to an exploratory analysis, that's where p-hacking causes problems. Outcome switching, I have an example of outcome switching that we'll talk about. Outcome switching is just when you design a study around an outcome and you have several secondary things you want to collect just to generate hypotheses. You find something really interesting in one of those secondary outcomes and you report that it was a kind of a confirmatory analysis when in fact it was not, it was exploratory. Selectively excluding data, for the same reason missing data can cause problems, excluding data can cause problems. And as far as interpreting findings, that kind of actually gets back to a lot of the things I talked about in terms of testing hypotheses. You just have to make sure that when you interpret your findings, that you're aware of your study's limitations. You're aware of your study's strengths and limitations, and you should not be stating that something is confirmatory when it's exploratory. Forgetting the context. Harking is kind of like phishing. It is hypothesizing after the results are known. So generating data and then looking at it and go, oh, that's a cool hypothesis, let's report that along with the p-value and say it's confirmatory. There are lots of flaws in that can cause problems with reproducibility. And of course, publishing and disseminating results. We'll talk about publication bias. It's a huge problem that we are all participating in, unfortunately. So, all the ways we can mess this up, and this is just a few of the more well-known ways. I would encourage you all to take a look on your own at some of these if you're not familiar with them. But these are the ways we end up producing research findings that are not reproducible in future studies. And this, again, is not, we can't point the finger at any one system. I think it's just built into our system. It is an us problem. For instance, the journals participate this. Historically, researchers, we publish in journals. The journals are for-profit, slowly changing, but because they're for-profit, they have in the past prioritized impact, newsworthiness over rigorous methods. They really like novel research and they really like positive findings, small p-values. We're much more aware of this now than we have been in the past, and so these things are getting better, but they're not completely fixed. Institutions also play a role. Those of us who do research, sometimes when we think about our career trajectory, quantity can trump quality. But some places, bigger is better, many are better than one. We also have this flawed idea around journal impact factor as a proxy for quality. In my opinion, and the opinion of many others, it's a big problem if you look at how these journal impact factors are derived, and it should not be used as a proxy for quality. Funders can also create problems or barriers to rigorous science in that they tend to not want to fund replications. So a study's been published, it's been conducted and disseminated, and it needs to be replicated. It's impactful Should we change practice based on a single study? What you'll learn if you look into this is that the original creators of experimental design, those that proposed the p-value, never intended it to change practice from a single study. They intended 3 independent studies with statistically significant findings to be the gold standard of practice-changing evidence. But that's not the way that it works. So they tend to not like to fund replications. It's already been done. But it's important that replications occur. They also don't necessarily fund systematic reviews, which we'll learn about as well. In terms of the hierarchy of evidence, systematic reviews and meta-analyses sit at the very top of the hierarchy of evidence. They're the strongest ways that we can evaluate what the current state of evidence actually is. And us, so how can we be better? Well, we need to know about all of the ways that we can fool ourselves, hypothesis myopia being one. So it's almost understanding a little bit of human psychology and fighting against it. Another thing that we can do is increase our education and training in probability and statistics, especially these tools that we use all the time in our own research or in our evaluation of the literature that we really don't understand. So have conversations, discuss these things with your collaborators, your peers, until you do have a better understanding of things, especially things like p-values. Because if we're going to use something, we need to understand its purpose, its strength, and its flaws. We can't operate in silos as well. So find experts. We are not experts in everything, so we need to collaborate. Team science is where it's at. And then finally, again, back to the idea of methods reproducibility, we need to be transparent and open, not only about our methods, but about our decision making, written justification of our decisions, because subjectivity is a huge part of science. And if there are flaws in our thinking, we need our peers to identify those. There's, again, a lot of talk about reproducibility, and one aspect of that is how we fool ourselves and how we can stop. There's an article in Nature about this that will get you thinking about the ways that you can identify self-deception and fight against it. And again, the first step is just knowing what we don't know. It's often those things that we don't know that derail us, that cause us to perform research that will not be reproducible. So awareness is the cure. We have to seek out and improve our training in scientific thinking and research integrity. We need to place greater emphasis on quality over quantity, quality over significance, because even non-significant findings are important. And we have to prioritize learning about questionable research practices. So, being a Star Wars fan, I'm going to leave you here before we get into the next piece with a quote from Master Yoda. Our plan for the rest of these lectures is to unlearn some of what we have already learned. And we're going to begin with the p-value. The p-value being a metric that's directly related to internal validity of a research study. Before we know what a p-value is, we have to understand what a p-value was designed to do. And a p-value really is associated with what are called experimental designs. And it's hard to introduce all of these topics at once. We will talk specifically about what it means to be an experimental design. An experimental design in clinical research is really just a randomized controlled trial. That's the only kind of design that's truly experimental. So p-values really are only supposed to be used in settings where randomization was used. That's when they are confirmatory evidence. They are also used as exploratory evidence, but sometimes that gets lost in translation. So when we think about experimental design, what is it? It is the process by which we protect the internal validity of a study. You can also think of it as the ways in which we attempt to account for or control the variation in our study's outcome. It's also, when we account for or control variation in the study's outcome, we're also minimizing sources of variation that produce errors in the data. So the way that this works is we, again, have that testable hypothesis. It usually starts very broad, and we narrow it down. And this, giving it one sentence does not really do justice to this process. It's a whole undertaking to get to specific testable research questions. Once we have those specific questions, then we have to think about how we are going to approach testing them. So we have to identify the conditions of interest. Usually there's at least one, but in an experiment there's at least two, one of them being a control group. What measurements are we going to collect on the units in the study, whether they're animals or humans? When are we going to take them? How are the conditions? We have to really do a good job of explicitly defining those conditions and how long they're going to, what's their duration, how are we going to make sure that the conditions were actually applied appropriately? So kind of in the terms of a clinical trial in humans, are the participants in the study, are they actually taking the medicine as they're supposed to? So it's kind of a compliance issue as well. The type of study that's ethical and feasible, we want to pick the strongest one that meets those requirements. Randomization in an experiment, randomization is used, how are we going to randomize, and so forth and so on. And then once we've got that plan, then we start to try to break our design. How can we mess this up? And we're doing that by identifying other potential causes of outcome changes in these participants. And how can we minimize them? So for instance, in a study, a randomized controlled trial, where I know the patient's gender is going to cause them to respond either better or worse to a particular treatment, or maybe just increase, maybe women are much more variable in their response than men, then I want to figure out how am I going to account for the sex of the participant in the evaluation of the association between the treatment and the outcome. One of the ways I could do that could be that I limit my study to only females. With any decision, there is a benefit, and that is I'm controlling that important source of variation, but there's also a cost to that decision. And the cost is, when I get done with this study, this valid result can only be applied to women. So you have to think about the benefit of a decision and its cost, and look at all the potential choices that you could make and find the one that has the best cost-benefit trade-off. So identifying those sources of variation, we either need to, if we know about them, we need to account for them in the way that we allow participants on our study. We need to exclude participants on the study according to those features, or we need to measure. We actually need to measure that and maybe account for it in the statistical model. Or we could set up our design so that randomization can account for that variation in the outcome. All of this leads us to a suitable study design. Once we get to this point, then we have to think about minimizing another important type of error. And it's one that we don't ever really, I think, personally talk directly about. We talk about, well, how many participants do I need in order to answer this question? What you're really asking is about a very specific kind of error called sampling error. And how can I minimize that source of variation in the outcome so I can get a valid result? So what is sampling error, and how is it a problem that we can overcome in study design? Sampling error is a really easy thing to think about. So anytime we're performing a study, we're really trying to get at the truth. The problem is we never can directly observe the truth. We just get kind of an incomplete snapshot using a sample of individuals from a population. I'm going to give you a contrived example here where we know the truth. Suppose the truth is that there are only 2,231 patients at risk of death due to a condition. So that's the entire population. The cool thing about this is, since this population is relatively small, if I am able to get all 2,231 patients to participate in my study and agree to being randomized between a placebo group and this active transfusion therapy intervention, then I can get the true impact of this active therapy relative to placebo therapy. What you often see when you're after these what are called binary outcomes, like whether an individual lived or died during a certain period of time, is this contingency table. So what we see here is we have two columns, one that describes the results of the placebo group and one that describes the results of the transfusion therapy group. So all 2,231 participants were randomized equally between these two groups. You can see we ended up with one more placebo participant than transfusion therapy participant. And this top row, that's the number of deaths among those 1,116 placebo participants. So 275 out of slightly over 1,000 in the placebo, 228 out of slightly over 1,000 in the transfusion therapy group. And when we have this kind of data, we often report the mortality rate or risk, and that's just dividing. You divide the 275 out of 1,116. That gives you the percentage or proportion of placebo patients that died, about 24.6%. Same thing for active, 228 divided by 1,115, that's about 20.4%. So just looking at this, we see we ended up with a 24.6% mortality rate and a 20.4% mortality rate in the active. So slightly higher by about 4% in the placebo compared to the active group. And this is the truth, right? This is the truth because this is every patient, and this is an accurate measurement of whether they lived or died, and this is an accurate description of the therapy that they actually received. The way that we might want to summarize the effect of this active therapy is to look at the reduction in mortality rate. And when we have percentages like this, we don't necessarily just subtract and say it was about a 4.2% reduction. That's like an absolute reduction. We want to look at a ratio. And so we take something called a risk ratio, where we take the risk in the treated group and divide it by the risk in the untreated group. And that ratio is 0.829. So how do I interpret that 0.829? If the risk was the same in both of the groups, then the number on the top of this numerator, the top of this fraction and the bottom of the fraction would be the same, and we'd end up with a risk ratio of 1. So risk ratios of 1 are kind of like differences of 0. So you have no difference here. If it's less than 1, then that means that the risk on top is actually smaller than the risk on bottom. So you have a reduction in risk for any risk ratio that's less than 1. And so the difference here, the impact here, is kind of how far away from 1 is this risk ratio. And if I subtract 0.829 from 1, then I get about a 20% reduction in risk. In fact, more specifically, it's 17. So it looks like this transfusion therapy reduces the mortality rate in this population. That's the truth. But again, we are never able to get an exact representation of the truth for many reasons. Number one, our patient population might be very large, or we might not be able to contact every patient in the population. Some of these individuals might not have a phone number, or they might live somewhere, that we can't get access to them. So it's not feasible to get all of the patients in the population. Assuming it were, you're never going to get all of them to agree to be randomized to placebo versus transfusion therapy. So even if you could get a hold of all of them, they're not all going to agree. So there's one problem. Even if you could get them all to agree, you're probably not going to get all of them the exact same therapy. So the placebo, maybe they'll all participate in that accurately, but maybe the transfusion therapy, some of them didn't get as much or got too much, or the timing wasn't accurate. For many reasons, you kind of don't have an exact representation of the therapy, the treatment received. You might also not get an accurate measure of death. Some of these individuals, if you have to follow them, let's say for 18 months or 2 years, some of them will be what's called lost to follow-up. So we never see this perfectly. There's always error in our perception of the truth. And we accept that. We accept that. And again, any decision that we accept, there's a benefit to that. And the benefit here in this compromise of just using a sample from the population is that we can actually get an answer. That's the benefit. The cost is that the answer will not be exact. So in this compromise, we take, instead of all 2,000 patients, we take a random sample of about 10% of the population. That's a lot of the population, but only 216 patients. And we randomly assign them to either placebo or the transfusion therapy. We end up with 109 and 107 in those two groups, and we measure their outcome. And we end up with 22.9% mortality rate in placebo, 27.1% mortality rate in the active therapy. The relative risk for this sample then is 1.18. The result of this study, which by the way is a randomized controlled trial, that gold standard of evidence, randomization is used, blinding is used. We estimate an increase in mortality by 18%. What was the truth? The real truth is that it should have decreased by 17%. We have a complete reversal of the findings. Complete reversal, an 18% increase. Why is that? That's the consequence of sampling and, again, not being aware of the impact of sampling error. And so this cost, sampling variability, can be shown in 10 replications of the exact same study. So perhaps if we look, the study that I described, we'll call that study number 1, and it contained 216 participants, and this was the result, an 18% increase in mortality. Let's say I'm the PI for that study. My protocol is followed exactly by investigator number 2 at a different institution. They take another sample of the exact same size, apply randomization in the exact same way to a different set of 216 patients, and they end up with a relative risk of 1, basically 1.06. So I found an increase in mortality. Investigator 2 found basically no difference in mortality. Investigator 3 follows the protocol, different random sample, found a huge decrease in mortality. So what is going on? If this were done independently by 10 different investigators on different samples of 216 patients drawn from this population, and we're all finding something different. Some of us are slightly different, like investigators 6 and 7, investigators 7 and 8, but some of us are very different, like me and investigator number 10 and investigator number 4. We found huge increases in the relative risk. So what's going on? Just a reminder, the truth should be a 17% reduction, a relative risk of 0.82. But even when we're using randomization, we have a randomized controlled trial in a random sample, we have demonstrated that it's still possible to get internally invalid results. In other words, we don't mirror that clear mortality reduction in the population in our sample. So what's the cause? Well, the cause, first of all, is sampling variability. And the way that we cope with sampling variability is to make sure that we understand its potential impact ahead of time and increase our sample size. So our sample size, and we won't talk about the mathematical relationship between sample size and how much these results jump around from sample to sample today, but we will in part 3. Just know that it's inversely related. The bigger your study, the less these results jump around. So if we were trying to replicate a major finding in an independent study, this would not be a reproducible result because of sampling variability, even though everything else we did was correct. But if we appropriately sized our study, what we would find is if sampling variability was our only uncontrolled source of error, increasing the sample size minimizes the impact of sampling variability, and all of our relative risks start to look very similar. They're all going to hover around the truth, which is a relative risk of 0.82. They won't be exactly 0.82, but they will be very close to 0.82. So just like if you're a physician, when you treat an individual patient, that individual patient is not always going to respond exactly like your other patients. There's variability in their response. And the way you think about that variability is you try to think of, well, what's the source? Was it because of the family history? Was it their previous exposure and the way they responded to the same class of drugs? Is it their age? Is it comorbidities? Those kinds of things. And you try to account for that in your treatment of a patient. We do that using statistics as well. There are lots of ways we can cope with sources of bias, but also sampling variability. And the primary way we do that at the end is through calculation of the necessary sample size so these results don't jump around so much. And so your study is more likely to be replicated in future independent studies. So a couple of key principles before we get into this idea of sampling variability and its impact. Sampling variability is always a source of error, even in perfect studies. So what do I mean by that? Well, first of all, there are no perfect studies, simply because every study that is done in samples will have a risk of a false positive finding and a risk of a false negative finding. We'll talk about that again very shortly. Different samples, different studies will always generate different results, even if they're done in exactly the same way. Exact same protocol, everything is applied appropriately, but you have two different sets of patients. Those two different sets of patients, they vary, and their responses will vary, and that will lead to different results. What you hope is that you have accounted for this type of variation in such a way that it's small or minimized. All studies can be repeated. All that's required for repeatability is transparency, documentation, and openness, but not all studies can be replicated. Even the good ones, even randomized controlled trials, are at risk of not being replicated. But we know and we can quantify that risk through things like the type 1 and the type 2 error. So when we think about when we're doing a study or when we're reading a study, this idea of what's its chances of being replicated? How likely is an individual study to be replicated in the future? The problem is we could kind of see visually the impact of sampling variation here and the fact that these samples did not produce similar findings. So there's a lack of replication here, lack of reproducibility. So how do we know that's the case if we only ever do a single study? How do we know if our particular study has a high chance of being replicated in the future? How do we know that the sample that we produced isn't just one of those samples that produced inaccurate findings? Like, for instance, my sample where we showed an 18% increase in mortality instead of a 17% decrease, even though I did everything correctly, right? I randomized, I blinded, had a control group. How do I know that my sample isn't that 1.18 as opposed to one that's closer to the truth? And the answer to that is the type 1 and type 2 error rates of your study. Assuming you've gone through the process of study design and you get down to that point where we've identified other sources of variation and accounted for them, the way that we then finally account for sampling variation, which again impacts our ability to replicate findings in a future study, is through controlling these error rates. The type 1 error rate is the false positive rate. It basically says if the truth is that there is no treatment effect, there is no association, what are the chances I'm going to find one? So it's a false positive finding. And type 2 is related to the power of the study. The type 2 is the false negative, which basically says, what if the truth is that there is a treatment effect, there is an association? What's the chance? What are the chances my study is going to miss that and conclude that there is no association? So type 2 error rate is the false negative. And again, it's related to the power. The power of a study is just the good side of the type 2 error. So it's if there is a difference or if there is an association, if there is an effective treatment, what's the chance I'm going to find it? And that's the power of a study. So we often, when we get to this point in study design, we often calibrate our sample size to achieve small type 1 error, small type 2 error. And what we're really doing is large power, because as type 2 error rates decrease, power increases. So again, if we have an experimental study where we've used all of those other tools in our toolbox, like randomization, blinding, control groups, if it's a rigorously designed experimental study, we can actually control these error rates pretty accurately. So we know ahead of time the approximate chances of our study being replicated in the future. If the type 1 error of my study is 5% and the power is 90%, then I know that the chances that if I find something, if I find an association, the chances that it's not real are 5% or less because of type 1 error being 5%. If I fail to find something, so if my result is that there's no association and my power was 90% and my type 2 error rate is 10%, so 90% and 10% add up to 1 or 100%. If I fail to find something, then there's a 10% chance that that's a false negative finding. That's what when we design our studies in this way, we can quantify it. So we know. And when we set those error rates, we set them in that way. How small do those error rates need to be for me to be happy, for this decision to be accepted by my peers? Before we get too far into pulling out what a p-value exactly is relative to sampling variation and what type 1 and type 2 error rates are relative to sampling variation, we need to talk about hypothesis testing, because all of these are the results of a hypothesis test. Without an actual hypothesis test, you don't have a p-value. Without a hypothesis test, you don't have power. Power is the probability of making the right choice when the right choice is that there's an association or a difference. So if you're not making a decision, using this kind of testing approach, then there is no power. We don't talk about it. But the premise in this basic recipe for hypothesis testing, again in the context of an experimental study where we're randomizing participants to either a therapy or a control, an intervention or a control, is that subjects who are treated differently should have outcomes that differ more than subjects who are treated the same. So if one subject received a surgical intervention and another subject received a surgical intervention, we would expect their outcomes in general to be more similar than comparing the outcomes of a subject who received a surgical intervention and a subject that received a pharmaceutical intervention. So bigger differences are associated with, bigger outcome differences are associated with different group assignments or different treatments. When we take a look at how outcomes vary, if two participants receive the same treatment, their outcomes are still different to some degree. And we attribute the differences in their outcomes to just the fact that these are two different people. Maybe one's 85 and one's 83, or one's 85 and one's 71. It could be one's BMI is high and the other one's is low. Maybe one's had the disease longer than another one. Lots of just differences between subjects. Some of those differences, some of those causes, we actually want to account for. But if we don't explicitly account for them, then we just lump it in and we just call it these natural variations. Sometimes we just call it the noise or the error in the statistics. If two subjects are treated differently, if they receive different treatments, their outcomes also differ, but they differ for two reasons. They differ for the same reason that the two subjects in the previous bullet point differ, those natural differences between them, either their age, anything that we're not controlling for, their age, their sex, their comorbidities, the duration of their disease, lots of things. So that those natural differences are still a source of variation, a source of the difference in their outcomes, but they also have that additional source, and that is the difference imposed by differences in treatment. And so when we do hypothesis testing, for those of you who have even a very basic applied background in hypothesis testing, we use something called a test statistic. For instance, in the t-test, what we do when we analyze the data that results from a comparison of two groups on their continuous outcome is we try to take the variation in these outcomes and assign it to a source, a cause. One of the causes is the treatment, and the other cause is what we call error, anything we didn't account for, those natural differences. So if you take a look at this simple formula of the t-test, what you have here is a ratio. You have a numerator that's doing something and a denominator that's doing something. And it turns out that the numerator is a signal. It's the signal of the treatment effect. Don't worry about the notation. What it's doing is it's measuring the difference between the observed outcomes, the observed average outcome of participants from what we would expect. Or in the case of a two-sample t-test where you have a treated group and a control, you might be comparing the average outcome of the treated group to the average outcome of the control. So that difference in those averages, we call that the signal. And when on the bottom, we try to talk or quantify the natural differences between subjects. We try to quantify that. And the way we quantify that is we just look at how do subjects who were treated the same, how do their outcomes vary? And that's measured by this quantity at the bottom. This is just a measure of the natural differences. And this top signal contains both those natural differences and the differences imposed by differences in treatment. So if the numerator is much bigger, if that signal is much bigger than the noise, then we have a big t-statistic, and again, for those of you who are familiar with the t-test, a big t-statistic is just a very big signal-to-noise ratio. So when it's big, it means you have a big signal for a treatment effect. And it's not just the t that works this way. The f-test in ANOVA is also a ratio. The chi-square test is also a ratio. They're just signal-to-noise ratios. Bigger is better in terms of a statistically significant finding. So how do we apply this back to our initial example for the made-up disease of hypohemia, which I didn't talk about, by the way. It's from a Simpsons episode. So what do? Well, if we follow the basic recipe for hypothesis testing, then we actually have to begin with an assumption, right? If you remember the scientific method, we begin with a hypothesis. A hypothesis is just an assumption. And we assume that there is no effect of this therapy. With that assumption in place, then we investigate the data. We look at the data to see whether or not the data agree with that assumption, or do they disagree with that assumption? And to what degree does it agree or disagree? So once we're going through this process, we're just determining whether what we observe in the data is similar to what we would expect to see if the treatment had no effect on mortality. We should expect to see a relative risk close to 1 if there truly is no effect of the treatment on mortality. The problem is, again, because of sampling variability, there's always a chance that that relationship will not be exactly mimicked in the sample. And that's, again, that type 1 error rate we want to control. If the truth is that there is an association, either it increases or decreases mortality, then we would expect to see that the sample reflect that by giving us a relative risk either bigger or smaller than 1. But again, there's always a chance, because of sampling variability, that it won't accurately reflect that relative risk not equaling 1, and that's our type 2 error rate, and we can directly quantify that. If we look at the example that we have here, these individual studies are each doing a hypothesis test. So in my first sample, I have a relative risk of 1.18. So if I just stop there and don't do anything else to acknowledge the impact of sampling variability on my result, I just report a relative risk of 1.18, and I state that there's an 18% increase in the mortality rate. But I need to quantify the impact of sampling variability so the people who are consuming this information can go, well, that might not be real, because there's a lot of sampling variability that's built into this relative risk. So it could be completely inaccurate. The way we quantify that is through something called a confidence interval. So when you see confidence intervals around statistics like this relative risk, they're just telling you the impact of sampling variability. So for instance, if my confidence interval went all the way down to 0.9 and all the way up to 1.3, what that's saying is sampling variability could cause me in this study, with this study size and these study parameters, it could cause other studies to produce relative risks anywhere between, 0.9 and 1.3. My study is just as likely to have produced a 0.9 or a 1.3 as it was to produce a 1.18. So it gives you an idea immediately of the quality of that relative risk estimate. Because within those boundaries, all the way down to 0.9 and all the way up to 1.3, I have anywhere from a 10% reduction in mortality all the way up to a 30% increase. That is basically non-informative, right? It could be no change, it could be a decrease, or it could be an increase. And I publish that. You focus on the 1.18 when you should be focusing on the confidence interval. You want the confidence interval all the values within it to be consistent in the messaging. So what we would hope to see is a relative risk of 1.18, as low as 1.1, as high as 1.23. All of those indicate an increase in mortality. And because it's a very concise, precise interval where all of the values within it convey basically the same message, then we have high confidence in the result. So if I were to produce a confidence interval for this relative risk, it would be very wide because of sampling variation. In fact, the confidence interval for this goes all the way down to 0.56. And I don't even remember the upper bound. 0.56 up to like 1.3. So clearly, if I had given you also the confidence interval, you would discard this finding right away. You would say, well, it's inconclusive. Sometimes, though, we focus on the estimated relative risk and the p-value that's produced from it. So what we would hope is that the p-value would also help us tease out that impact of sampling variability, but we have to understand what it's telling us. So in this particular test, the p-value, again, is the result of a hypothesis test, which requires a test statistic. And the test statistic, whenever you have mortality risk like this, is something called a chi-square statistic. Again, not getting into the math, it's not necessary. It's a signal-to-noise ratio. The bigger it is, the bigger the signal relative to the noise or variation in the data. So this statistic, this chi-square statistic, is helpful just as the t-statistic is helpful, in that we understand that the bigger it is, the further away from zero this t-statistic is, for instance, the bigger the signal. If this numerator, if what we observe in group 1 is the same as what we observe in group 2, then this difference in the top would be 0, and this t would be 0. In fact, if you take a look at this distribution, so Mary Ellen asks, please remind me what signal and noise reflect. The signal reflects the treatment effect. So if there is a signal, it means you're basically identifying an effective treatment. And noise is just error, just sampling error, sampling variation. So back to this picture, which for those of you who took like a stats class in undergrad, or maybe an introductory stats class whenever you were in grad school or medical school, you might remember drawing this and labeling some things out here on the ends and making a decision about a hypothesis test. And that might have been all you did. You didn't understand necessarily. I will tell you, I have a PhD in statistics, and when I took my first statistics class in undergrad, I had no clue what I was doing. I followed the recipe. And that's fine, but when you follow the recipe, then you're not able to critically think about the process and see when the data might be lying to you. So let's try to figure out how this is working. So this distribution is something called a probability distribution. So along the x-axis are numbers, numerical values, and it turns out this center value right here for this distribution is a 0. This distribution is called, you can call it, it's a bell-shaped curve. In some cases, it's a normal. In the case that I'm talking about right now, it's a t-distribution. And the idea behind a probability distribution is for a particular value of our test statistic t, the height of this curve, and specifically the amount of area under the curve in a particular range of values of t, corresponds to the chances of observing those values of t. So I don't know if this is a touch screen or not. Let me see. So this is a t of, we have values of t along this x-axis, where t is like the test statistic on the previous slide. This location is t equal to 0. This is the location this is the value of that t that I would expect to get if there's no difference between the two groups I'm comparing. So this is the test statistic I would expect to get if the null hypothesis is true. Remember, the null is basically there's no difference. As we move away from zero, either in a positive direction or a negative direction, the strength of a treatment effect is getting stronger because the t is getting bigger. How is the t getting bigger? The t is getting bigger because the numerator, the signal piece of that, is bigger. So as the signal gets bigger, the value of t I get actually either gets bigger in this direction or in this direction. So let's just pay attention to this side. Suppose I get a value of t that I calculate as 3 from my data. If I get a calculated value of t of 3, then I want to take a look at where it falls along the x-axis and place it there. And this, again, this distribution describes how likely it is under a certain reality or scenario, how likely it is that I will observe a particular value of the test statistic. And the p-value quantifies the likelihood of observing the test statistic that we actually calculated. So it's basically, what are the chances of observing a signal this large or something larger? That's why the p-value encompasses values of t that are further out in the tail than the one that we observe. So what are the chances of observing a t this large or something larger kind of corresponds to, again, what are the chances of observing a treatment effect this large or even larger under the assumption of the null hypothesis. So if there is no treatment effect, this is the chance that I would see this kind of signal in the data. That's all that it is. So in terms of interpretation of this particular test statistic, what it's saying here is that numerator, that signal, is 3 times as large as the denominator, the error. So it's a pretty large signal. The p-value will further quantify how strong the signal is by telling me about how many possible studies would produce a result at least this unexpected. So when we think about that, the p-value is quantifying, let me erase. There we go. The p-value is a probability that's calculated from this distribution, and it represents essentially the probability that the sample we actually have is not accurately representing the truth that there is no association. Let me say that again. The p-value, you can think of it as the observed risk of a type 1 error. It's calculated based on our observed data, so it's observed, and it quantifies the chances of observing this strong of a treatment effect if no treatment effect truly exists. So it basically quantifies our risk of having a misrepresentation in our data of a treatment effect. So again, let me pull it back to this specific example. So it's a little bit easier to understand how do we interpret it if I give you a number and then we say it in English. So remember, in our sample 1, which is, again, we pretended like there were 10 different independent studies done just to demonstrate how sampling variation causes the evidence to bounce around. How do we know that the evidence could be bouncing around if we just do the one study? And that is through the confidence interval, which we discussed, but also the p-value. So in our one study, we saw an 18% increase in mortality that was associated with therapy from a sample of 216 subjects. And this was a randomized controlled trial, so it should be pretty protected against bias because of randomization. So we know that if we found an increase, we know one of two things has happened. The sample's accurate and there really is an increase in mortality associated with the treatment, and that would be a correct decision, or there's a potential error that was made here. The sample is inaccurate and there is not an increase in mortality. So either there's no difference in mortality or a potential decrease. And so we have to figure out which of these two is the case, and the p-value helps us with that. So I calculate the chi-square statistic. I'm not going to go through the math. If I were to put this data into a tool, it would produce a chi-square statistic, one way of analyzing this data. And that chi-square statistic would correspond to a p-value of 0.25. So the way that you interpret your p-value, assuming you're in a randomized controlled setting, is that there is a 25% chance that this sample, this particular study, is inaccurately depicting an increase in mortality. There is a 25% chance, or a 0.25 probability, that this particular study inaccurately depicts harm. That's why a lot of times we calibrate our decision making to a specific probability. So for instance, ahead of time, what we often do is we pick a value, we pick a percentage or a probability that we're comfortable with. And 25% is usually not it. Because if you set your threshold for significance at 0.25, you're basically saying that you're comfortable being fooled 25% of the time. And that's not how we often like to operate. The most widely acceptable criteria is 0.05. In a lot of cases, it's appropriate. In some cases, it might need to be smaller or larger. But what you're basically saying, if you let the threshold be 0.05, is even before you conduct the experiment, you're telling everyone that you're comfortable being fooled 5% of the time. You're comfortable with a 5% false positive rate. And that's where the decision making comes from. So you can see it's more a continuum, right? It's a number between 0 and 1, chances between 0 and 100%. And so 5% is not always the optimal place for that level of comfort. You might want it to be even smaller depending on the consequences of a false positive finding. So the p-value helps us cope with sampling variability. What it does is it links the outcome of our single experiment to the types of samples that could have been produced, taking into account the level of sampling variation in the study. So if the p-value is large in this setting, it reflects large sampling variation. If the p-value is small, it reflects small sampling variation. The problem with p-values, though, is that we use them in this way, but we don't use them always in this way when we have a true experiment. We're using them in what are called observational studies, and we'll talk again next time about the difference between experimentation and observation, but it should be clear that experimentation exerts a ton of control over the setting in order to account for other sources of variation in the outcome. And so when you're not doing that, the p-value, this interpretation of the p-value is not correct. It's no longer the probability, the observed risk of a false positive finding. It's not, because it doesn't contain just sampling variability. It contains other kinds of variability, and then it breaks the interpretation. So what are experimental studies? Well, those are the most rigorous form of scientific investigation. You learned about this maybe in a high school science class. My children have learned about it in elementary school. And it's the most rigorous way we can undertake a scientific investigation. There is a design, some kind of logical structure within which the investigator systematically introduces changes into an independent variable and observes the consequences of those changes in the dependent variable. So you have a cause and effect, and you're controlling the independent variable in some way. And again, the purpose or the goal of an experiment is to support a cause and effect relationship where the independent variable, changes in the independent variable are causing changes in the dependent variable. The only type of clinical research investigation that is an experiment is the randomized controlled trial. And the reason why that's the case is because it incorporates within its design considerations for all of those other potential sources of variation in the outcome. So when you see changes in the outcome that are associated with changes in treatment, you can directly attribute those changes back to the treatment. So you can infer a cause and effect relationship. The ways in which we try to control those other extraneous factors are through the way we select the subjects to participate, how we apply the treatment through preferably some kind of random process, randomization, how we measure the outcome, and how we analyze the data. And again, the goal here is to isolate and detect the effects of treatment on the outcome. And all of these factors can contribute to variation in a subject's response that can impact the validity, the internal validity of our conclusions. So the ways that we, in an experimental setting for human subjects, approach protections against some of these biases are through some of these random processes, like trying to randomly select study subjects from the population. The purpose of that is to protect us against biases that result from systematic selection of study subjects. That's called selection bias. And it also ensures that we have a representative sample. So when we try to generalize our findings back to a larger population, we have external validity. So let's suppose we have a population, and in that population there's this characteristic that's denoted by the color of these individuals. Let's say that these individuals here have a particular type of mutation that causes them to respond better to treatment. If I did some kind of systematic selection, there could be physical characteristics of these participants that are associated with that mutation. And for whatever reason, here we go. Well, I removed a slide for the sake of time. I was going to show you how systematic selection results in a biased distribution in our sample. So here, if we randomly select individuals from this, we end up with that mutation's prevalence in our sample being equivalent to the prevalence in the population. So 30% of our sample has a mutation, 26% of the population has a mutation. It's about the same. If I were to do this more in a systematic way, where I'm selecting patients for my study based on some characteristic that happens to be associated with this mutation, I might get a higher prevalence of that mutation and make a therapy look better than it actually is, without really understanding that it's the mutation that's driving effectiveness as opposed to the therapy itself. So I don't know how to, let's see. All this says, for some reason I can't get my little thing here to move. If we use random selection, it's highly probable that we'll have a representative sample. And representative samples provide not only internal validity, but external validity. Randomization is the same thing. So if we have, again, a population of individuals, 30% of them 26% of them have this mutation. We have our sample, of which 30% has the mutation. I want to randomly assign them to the experimental treatment and the standard of care. And what ends up happening is randomization equally distributes the individuals with the mutation across the two treatments. So if these individuals are going to respond better in general, then I'm equally distributing those effects through the two groups. So then if the experimental treatment has an effect, I can tie the changes or the differences in their outcomes back to the treatment, not to the mutation. So this is protecting us against specific biases called allocation bias, nuisance factors like confounders, those kinds of things. So randomization and random selection are so important, probably two of the most important tools that we can use to protect ourselves against bias. And again, assuming that the groups are equivalent at the start of a study, assuming that they're equivalent in terms of these other potential sources of variation like this mutation, allows us to be confident that any differences between the two groups in terms of outcomes at the end of the study are attributed to the treatment and not to the differences in the groups that existed before treatment was applied. Another approach that we might take if we have a source of variation that we know could play a role and we know about it in advance is we might want to block on it. So blocking is just another way of controlling for a potential confounder or source of error explicitly in the way we randomize. So suppose we have a large multi-center clinical trial that's going to enroll 1,000 patients across 10 clinics or 100 clinics. Each clinic is charged with enrolling 10 subjects. And within the clinic, what we do first is we block based on clinic. And then within the clinic, we randomize the participants 50-50 to the intervention or the control. Why do we do that? If we put everyone in clinic 1 in the intervention, everyone in clinic 2 in the control, let's just suppose we just have the 2 clinics just for simplicity's sake, then at the end of the study, if I see differences between the intervention group and the control group, I cannot determine whether those differences in outcomes are because of the intervention versus the control or because of the clinic 1 versus clinic 2. This could be the VA, and this could be KU Med. Is it the institution that's the difference in patient outcomes or the treatment? There's no way in that particular approach I could tease out the effects of the clinic that's accruing patients. So blocking is one way we can explicitly account for a source or more, one or more sources of variation in the outcome explicitly in the randomization. Otherwise, we allow randomization to account for those kinds of things on its own. And again, the control groups, this is, I think, pretty clear, but we need to make sure we're picking the right control groups for our research question, depending on what kinds of biases we think might exist in our assessment of the effect of treatment. So in some cases, if it's ethical, we might have what's called a null or untreated control, and the purpose of that control group is that it allows us to identify how the disease or condition is progressing naturally over time. And if we don't have a null or untreated control, then we are not able to observe that natural progression of disease, and we might attribute that change in disease state to the treatment, when in fact it's really just the disease resolving on its own or getting worse on its own. If we have a placebo control, that just eliminates biases that can arise from the act of being treated or potentially the inactive ingredients in a drug that may or may not have effects. They shouldn't, but they may. And then, of course, we on a lot of clinical trials, we have what are called active controls. A lot of times it's the standard of care. And those are great because if it's a standard of care, we know how these patients are supposed to respond. So if the standard of care arm in our study, if the patients aren't responding the way that we would expect them to, it allows us to determine issues with our particular study. So if they're supposed to respond 20% of the time and they're responding 0% of the time, then that might be an issue with our internal validity. Something might be happening. It also allows us to eliminate biases that can arise from factors other than the treatment condition. So here's an example of that null control where if they're not treated, then what we see is the outcome increases by a point from baseline to 12 weeks. And if we weren't able to see that change, then we might attribute it to the treatment. So we would kind of need to calibrate this treatment effect for the potential effect of just the natural progression of the disease. So observing it by itself, we see a change of 10 in treated patients, a change in 1 in untreated patients, and we'd need to subtract it out. I'm going to, for the sake of time, skip this. This is just talking again, reiterating about signal and noise, why patients respond the way that they do, why their outcomes might vary, whether it's due to what's called sampling variation or experimental error, and then the idea that there's an effective treatment along with experimental error. And finally, blinding. The purpose of blinding is just to eliminate the impact of any biases that could arise from the knowledge of treatment assignment, like if you're a participant on a study and you know you're randomized to a treatment and you're really excited about that, that might impact the way that you respond. If you know you're assigned to another treatment that you are unhappy with, then that, again, might negatively impact the way you respond. It might also cause you to drop out of the study and result in missing data, systematic missing data, so that would result in bias. There's single blind, double blind, triple blind. Triple blind is when whoever's doing the data analysis is blind, and we like that as a big part of reproducible research. Other protections against bias. So if you're doing a clinical trial, one of the major weaknesses of a randomized controlled trial, which we think of as the gold standard, is it might be at risk to what's called loss to follow-up or missing data, missing outcome data, because these participants have to agree to come back for further evaluation and may or may not do that for whatever reason. And so that missing outcome data can result in bias in the estimate of the treatment effect. And there are some ways that we account for that. One of the most widely accepted ways that we account for that missing outcome data is the way that we analyze the data. We can do it in 2 ways, using something called the intention to treat principle or a per protocol analysis. So the intention to treat principle actually, when we have a study like the one where we're hypothesizing whether or not there's an increase in mortality, if we analyze the data using the intent to treat principle, it can protect us against bias. It basically gives us a conservative assessment of the effect of treatment. So what we do is we analyze the individuals as they were randomized, regardless of which treatment they actually received. We measure the outcome data on all the participants, and we make some assumptions in the process, and then we include all randomized participants in the analysis, regardless of whether or not they ended up getting treatment. And again, that provides a conservative assessment of treatment effect. A more, when I say conservative, I mean it tends to, it does not overestimate the effect of treatment. A per protocol analysis it gives you really a more precise look at how the treatment worked in subjects who were treated according to protocol. So this one tends to not translate to the real world very well because not all patients who will eventually be treated will be treated according to protocol. So the per protocol analysis compares treatment groups using only data from subjects who were treated according to protocol, and it tends to provide an overly optimistic view of treatment. So visually, in a study, we have people randomized to treatment or standard of care. We have some that comply, some that don't in each of the groups. The per protocol analysis just compares the compliers. The intention to treat analysis compares everyone. And again, it might have to impute or make some assumptions about the missing data in the process. So how could we inadvertently screw this up? If we are conducting a randomized controlled trial and we're accounting for sources of variation through the study design, a rigorous design, we're also accounting for sampling variability through control of our type 1 and type 2 errors. So we're doing everything right. There are other ways that we can mess things up. And these other ways are known as questionable research practices. The problem with questionable research practices is that we don't talk about them as much as we should. In fact, some of them are passed off as valid research practices from mentor to student, and then this issue persists. So one of the ones I'm going to talk about is outcome switching. And I'll show you how outcome switching messes up our chances of producing reproducible research. In other words, it impacts our p-value. And so our p-value is no longer a measure of just sampling variation, it's a measure of sampling variation and something else. So suppose, again, we have 3 investigators independently performing their own studies. Their studies are done in a way, they're very similar. They're all interested in progressive deterioration in heart function in patients with mild congestive heart failure. All 3 of them pick the same primary outcome because it's well accepted that this outcome, left ventricular ejection fraction, is the outcome to work with. It's the gold standard. So they design a study around it, and they power the study such that, or they size the study such that the type 1 and type 2 error rates are controlled for testing a hypothesis about left ventricular ejection fraction. They're also, though, they want to generate hypotheses for future study, right? Because we recognize that study needs to continue, and there might be important features that, or artifacts that show up in other measures of dysfunction, like the in diastolic volume, in systolic volume, and so forth and so on. So they're going to collect those. Those are known as secondary outcomes. But the study is designed around controlling the false positive and false negative error rates for LVEF. In study number 1, investigator 1 finds no change, no important change in the primary outcome, LVEF. However, when they look at that secondary data, they find that the in diastolic volume did change substantially. So what do? In the publication of the study, they focus on EDV. And they don't say that LVEF, that the study was designed for a different outcome. They just report the EDV findings. Investigator 2 does the same thing, but for a different outcome that happened to show up with a substantial change, and that was the in systolic volume. No surprise, investigator 3 did the same thing for SV, but none of the others. And the problem is, in disseminating this result, nobody did their due diligence in terms of having that first characteristic of rigorous science, in that it is methods reproducible. They were not transparent that their study had a prospectively identified endpoint of LVEF. And they also didn't report that it was a negative finding. They cherry-picked the results. This is called outcome switching. The problem with outcome switching, and again, it's used all the time, that the problem with outcome switching is it invalidates your type 1 and type 2 error of your study because it contaminates the p-value with a second source of variation. How do I know it does that? Well, if you think about it, the decision to change the endpoint was driven by the random data. It was a data-driven decision. The random data were permitted to convert their design, their fixed research plan, to a random plan. Random data produces a fortuitous change in EDV, so now analyze this randomly chosen endpoint that was selected by the data. So the p-value that's produced by the test contains two sources of variability. It contains the sampling variation, just like we described before, but now it also contains this variability of endpoint selection. So the non-sampling variability that results from endpoint switching or outcome switching destroys the interpretation, and that p-value is no longer the chances that the sample produced a result that is misleading in terms of showing a finding when a finding really isn't there. And so again, the p-value is linking an experiment's outcome to the types of samples the population or process produces, but when there are other sources of variability, it's not doing that anymore. It cannot be interpreted in the way that we have already described. So what does that mean? That means if you're using a p-value in that way as a measure of confirmatory evidence that a hypothesis is confirmed or refuted, it has to be the result of a well-defined, well-designed, prospectively fixed experiment. Experiment also being the key. So it has to employ randomization and all other principles that protect us against sources of variation. The only random component allowed is the data itself. There is also another important thing to think about when it comes to the p-value is that there's really no theoretical justification for p less than 0.05. It's an arbitrary decision rule. It actually is just there because of tradition. So you're welcome to think about the type 1 error rate not being 0.05. If you understand that what it's basically saying is you're comfortable being fooled into thinking that there is an effective treatment 5% of the time. The chances that your study are going to produce a false positive finding, in other words, an association when there is no association, is 5%. Think about the consequences of a false positive in your specific setting. 5% might be too large. It might need to be 1%. It might be too small. It might need to be 10%. Think about the consequences of a false negative finding. The generally accepted principle for power is 80 to 90%. That might not be large enough. Think about the consequences of a missed treatment effect. What are the consequences of shelving something that is actually promising? What are the consequences of moving forward with something as if it's promising when actually it has no effect or it has the opposite effect? Another thing to think about when it comes to p-values is they're not to be used as a measure of effect size. They simply provide us with an estimate of sampling error and how it impacts the findings. In other words, it tells us a little bit about how much the statistic, the relative risk, is likely to jump around from study to study. If the p-value is small, it means that the sampling error is pretty tight. There's not a lot of it. But if you're overpowered, if your study is huge, the p-value could be small simply because you have, when you increase the size of your study, you decrease sampling error kind of artificially. You can decrease it to very, very small levels, and your p-value will quantify that. So overpowered studies are likely to produce smaller p-values simply because they're large, not because there's a clinically meaningful effect. So make sure you focus on the actual difference or association that you observe and think about it in terms of its clinical meaning as opposed to its statistical significance. So how do we protect ourselves? A lot of, and you'll see this already, if you're doing clinical research, you have to pre-register protocol. And in your protocol, you actually pre-specify your outcomes, you pre-specify your hypotheses, you pre-specify your error rates, and you have a pre-specified analysis plan. Stick to it. It's important that if your study was designed to answer a specific question, it will produce valid evidence for that specific question, but not necessarily for other questions. Other questions should be considered hypothesis generating, not hypothesis confirming. Perform data analysis blind. And again, place greater emphasis on the quality of your research as more than the significance or the novelty or the quantity. That's a protection that we can put into place. And finally, other types of questionable research practices that can cause even great studies to lack reproducibility, the idea of outcome switching, changes to the analytic plan. They happen, unfortunately, but you should recognize that changing the analysis plan or the analytic plan can impact your type 1 and type 2 error rates. Harking and p-hacking both have to do with, and you know, when we talk about how harking, which is hypothesizing after the results are known, and p-hacking, we're talking about passing off hypothesis testing and p-values from secondary or exploratory analyses as confirmatory. That's the problem. Specify they're exploratory and then publish them as such. The key is the educated reader will know, well, this was exploratory, so I'm not going to like change practice. I'm going to wait. It's interesting. I'm going to think about that whenever I'm practicing and whenever I'm observing. Now I've got that important information in my mind, but it's not going to be of the level of evidence that would require me to change practice until I see prospectively designed studies to address those hypotheses in a valid way. I'm going to skip through that. Some more resources again when it comes to these topics. Just to reiterate, the example that I pulled today was from a very, very good, very short textbook. It's not even a textbook, it's a book called The Intuitive P-Value Primer. It's written by an MD who's also got a PhD in biostatistics, so he's able to translate some of these topics to a clinical and translational audience in a way that someone with just a PhD in statistics may have difficulty doing. So a lot of stuff, and these also clearly link out to other topics. Next time in part 2, we're going to, so now that we kind of understand the importance of context and how we can ensure reproducibility by picking a really strong design and not going through with any questionable research practices. We have a better understanding of how to interpret findings in the context of sampling variation. Now we're going to talk about the hierarchy of evidence, because not everything can be an experimental design. We can't always do a randomized controlled trial. So observational studies are just as important and oftentimes the best that we can do, because randomization is not ethical or feasible. So we need to understand our options and how each of the particular study designs are set up in a way to strengthen particular assessments. And unfortunately, because of the way they're set up, they also have certain types of flaws that we need to be aware of when we're evaluating the results from them. So next time we'll pick up with study designs. We'll talk about the randomized controlled trial, cohorts, case control studies, cross-sectional studies, and ecological analyses. We'll also briefly touch on meta-analysis and systematic review, and go through a couple of examples. If you're interested in reading more about this ahead of time, you're welcome to take a look at this article from 2016 about this pyramid structure for the hierarchy or quality of scientific evidence, and how it's a little bit misleading to just draw a line and assume that all cohort studies are inferior to all randomized controlled trials, because that's not always the case. A really good cohort study could produce higher quality evidence than a lower quality clinical trial, randomized controlled trial. Take-home points, sampling variability. Even if we do everything right, we still have to try to take into account its impact. If we're not the one conducting this study, we need to look for indications in the literature that sampling variability was controlled. Look at confidence intervals. Confidence intervals are the best look at the impact of sampling variability. And the p-values, if they're the measure of sampling variability of its impact that's being reported, you need to make sure that it's appropriate. Was it a randomized controlled trial? Did you think, based on their inclusion-exclusion criteria and the description of their methods, that they accounted for all the important sources of error? Or is it possible that p-value is misleading because it's not the result of an experimental study? Are they reporting p-values as confirmatory evidence when they should be reporting them as exploratory or hypothesis-generating results? Not all studies can be replicated. Even a quote-unquote perfect study has false positive and false negative error rates. We want to control them to be small, but there's still a small chance that that finding can't be replicated, even in the best randomized controlled trials. But all studies can be repeatable. That's in our control, to be transparent, to be organized, to have written justification of our decision-making and changes, and to share our methods, our data, our code, to pre-register protocols, and don't engage in questionable research practices. And finally, the p-value and other experimental design concepts. This was developed with the idea that one high-quality randomized controlled trial, one high-quality experiment isn't necessarily it. When possible, we need to try to replicate this high-quality evidence in another independent high-quality study, because two randomized controlled trials that produce similar evidence provide us with higher confidence in the finding than just one. Another recommended reading provided here. A reminder of the KUMC resources. We do have opportunities to come to lectures like this in summers. We also offer a seminar series and a journal club. You're welcome to contact our department to get information or get on those mailing lists. We have coursework, certificates, degree programs for those who are interested in more formal training in that. We have a student tutoring lab. You're welcome to reach out to me for information about that, where if you're a trainee or a student, you can come in and discuss some of these issues with a PhD student in biostatistics, get help with your homework, get help with your research project. We also have a lot of faculty in our department who are available to be mentors on grants or fellowships, training grants and fellowships. And we also do a lot of peer collaboration. So again, make sure that you're aware of the resource that is provided to you by the institution and by the department, and use that resource as much as you can.